Hello, my name is ChrisMarble, and today I will be covering problem 4.22 and the concepts behind problem 4.22. Let's begin by looking at the problem. A very long cylinder of linear dielectric material is placed in otherwise uniform electric field E0. Find the resulting field within the cylinder, given that the radius is A, the susceptibility chi, and the axis is perpendicular to E0. The outline for this will be to discuss linear dielectrics and the boundary condition of linear dielectrics, and also to look at separation of variables for cylindrical coordinates. Once both these concepts have been covered, then we can solve problem 4.22. The first part is over linear dielectrics. We begin by thinking about polarization. Now, polarization is a macroscopic property caused by the individual dipoles, electric dipoles that form when an electric field is going through your dielectric. So the polarization is the macroscopic property. We use capital P for that. And we can describe these bound charges that are in terms of this polarization. So we can say that there's a bound volume charge, which is equal to minus the divergence of the polarization. And we can say that there is a bound surface charge, which is the polarization dot the normal unit vector pointing out of the surface. Now, if we say we have a linear dielectric, then we've added an additional condition. We said that now the polarization P is now linearly related to the electric field in the dielectric. So we can say that P is equal to epsilon naught chi E. And so we can now say that the permittivity of the material is just defined as the permittivity of free space times this 1 plus chi E. Chi. And chi is effectively the determined by the dielectric you have. So each different type of material you get will have a different dielectric constant, and that susceptibility constant is what we call chi. Now, using this, we can rewrite D. We can recall the definition of D was epsilon naught E plus the polarization, and then we can put this in and put that as our new electric displacement. So now that we've rewritten the electric displacement, that can be useful, and we've also rewritten P in terms of E, which is useful. So if we go back and look at the bound volume charge, equation 4.12, we can now rewrite it in terms of D, the electric displacement. The reason that's useful is we often do not control the polarization, but we do control the free charges we put on our object. That's usually what is controllable. So we can rewrite it minus the divergence of P becomes minus the divergence of epsilon naught chi the electric displacement over epsilon, and that is just substituting 4.30 and 4.32 into 4.12. And then we can go ahead and move the divergence through the constants, and then remember that the basically free volume charge is equal to del dot D. And using that, then we can go ahead and rewrite the bound volume charge in terms of the free volume charge. So we find it's minus chi E over 1 plus chi E times the bound free charge. The free volume charge. And we will note this result as 1 because this result is going to be useful in our problem. The next thing to look at is the boundary conditions. The first boundary condition is unchanged and boxed, as it will be needed. It basically says that the voltage is continuous at the boundary. And the reason the voltage is continuous is the voltage is the integral of minus the electric field dot dl. And if we take a path just crossing that boundary, we can take it basically an infinitely short path, so the integral goes to 0. So even though the electric field may be different inside and just outside the boundary of the linear dielectric, we know that the voltage cannot be different at the surface of linear dielectric. It has to be continuous. Additionally, we can look in terms of the electric displacement. In Chapter 3 and 2, we discussed the electric field perpendicular out minus the electric field perpendicular in equals the surface charge divided by epsilon naught. Well, now we need to look at it in terms of the electric displacement and the free charges. And again, we want it in terms of voltage, since we are going to want it to look like the first boundary condition. So we will write D in terms of E and substitute that in, and then write E in terms of the partial of V with respect to N, where N is the direction of crossing the boundary. So on a cylinder coming out radially through a cylinder, you would find that that would be the S of a cylinder. And when we plug this into our equation, we get epsilon naught, the partial of V out with respect to N, minus epsilon, the partial of V in with respect to N, equals minus the free charge on the surface charge. And this is a boundary condition in general. However, if we also say that there is no free surface charge, we can write a bit cleaner. And this is the form we will use because in our problem there is no free surface charge. However, boundary condition 2 holds in general, while the equation 3 only holds in that special case. Part 2 is on separation of variables for cylindrical coordinates. We recall that in the book in Chapter 3 it discussed deriving it for both Cartesian coordinates and in spherical coordinates. However, cylindrical was left out. Hence, we need to derive the general solution to the Laplace's equation in cylindrical. To do this, we have to begin with the condition of using Laplace's equation, which is that rho is 0 inside and outside the cylinder. The reason for this is that del squared V is negative rho over E naught. To make del squared V 0, we need rho to be 0 inside and outside. And that's what we have now. With that assumption, we can go ahead and say del squared V is 0. However, we also should say that the cylinder is infinitely long. If we fail to do that, then the voltage will change depending on Z, and that's not interest. So, saying it's an infinitely long cylinder, we can break V into a function of G of S, called G of S, and a function of V called H of V. And we need now to find G of S and H of V and solve Laplace's equation. So using cylindrical coordinates to write del squared V, and then we can go ahead and just plug in the G of S times H of V and write it out, pulling out the term that does not depend on V and on S respectively. And then we can multiply by S squared over GH, and this separates the terms into the G and the H effectively. And now that we have it separated, we can now write it in terms of two separate equations. This lambda is chosen intentionally. Now, our choice will make sense in a moment. The first equation is not perhaps as clear or well known, but the second differential equation should be very familiar from Physics 1. So looking at that equation first, we need solutions that are periodic. Because let's just say you decide to go around the cylinder and you start at phi equals 0 and you decide to walk around the cylinder and come back to phi equals 2 pi. Now, if you do that, you can't change the voltage by doing that. You have to have the same voltage if you go around the cylinder and come back to the same point. So we know that h of 0 needs to be h of 2 pi, and h of pi needs to be h of 3 pi, and so on and so forth. So we know we need periodic functions. Sine functions periodic, the cosine functions periodic, but exponential functions are not. So we know that the lambda being negative case would be problematic, as that would get us exponential solutions. Now, if we look at the lambda equals 0 case, it works if we only use a constant. We can't have a constant phi times phi, because that phi would be increasing and it would not be a periodic function. So we can include that by just writing it as a cosine lambda phi plus b sine lambda phi because that includes the lambda greater than 0, which is the sine and cosine solutions, which are periodic. And also for phi equals 0, lambda equals 0, it just simplifies to a constant, and that's okay as well. So we'll write that as equation 6, and that is h of phi in general for this problem. Now it's time to go back and look at equation 4 and look at g of s. Looking at the lambda is not 0 case, we need to note that this is a type of differential equation called a Cauchy or Euler differential equation, and similar to how when you look at equation 5, the h of phi equation, differential equation, you can say, oh well, I know to guess that h of phi is ae to the lambda t, and that'll solve it. Similarly, we look at this one and we say, what's the guess for this particular function? And the correct guess would be to say, let g of s be s to the n. And so that's what we're going to do. If we plug in s to the n for g of s, we get the differential equation below. So we get s times the derivative with respect to s of s times the derivative of s to the n over s ds equals s to the n times lambda squared. And this is for the non-zero case. We'll have to handle the zero case separately, as we'll see why in a moment. So we can go ahead and take the derivative of the interior, and that simplified it a bit. And then we can go ahead and take the next derivative, and that lets us get this equation to a much cleaner state. So we see n squared equals lambda squared, and recalling that these are natural numbers, this just shows us that basically lambda is going to be plus or minus. So n's plus or minus lambda. So we can write g of s as equal to d s to the lambda plus e s to the minus lambda. And our advantage is we know lambda already, that lambda is going to be 1, 2, 3, 4. We don't have to look for lambda now. And this is equation 7. We've solved it for lambda not 0. But now we have to come back and say, what about the 0 case? Because if you look at this equation, if we plugged in lambda equals 0 into equation 7, we would just get g of s as a constant. And we know there need to be two solutions for lambda equals 0. So we need to go find it especially, because it doesn't come out of that equation 7 directly. Looking at for lambda equals 0 case, we'll just take equation 4 and plug in lambda squared equals 0. And that lets us, we can multiply by g over s, and that cleans up a bit. And then we can look at it again and say, well, the derivative with respect to s of the inside is 0, therefore the inside of it has to equal a constant. I'll call that f. So we know the inside equals f. We can move the s across the equation to the denominator, and we can integrate, which is what we'll do. And that gives us equation 8. And looking at equation 8, we have a constant times the natural log of s plus another constant, and that's for the lambda equals 0 case. If you think about that, that's basically the logarithm would be like a line charge. You might see the logarithm of s. And so looking at that, we now have g of s for the lambda equals 0 case. We found g of s for the lambda greater than 0 case with equation 7, and we knew h of phi for all values of lambda 0 and greater from equation 6. So combining equations 6, 7, and 8, we can write the voltage by multiplying g of s times h of phi for every lambda value and adding them together. And that gives us this rather long equation. We have basically that a cos 0 plus b sin 0 is just a constant a, so we can multiply that into the g plus f, the natural log of s. We also have an infinite sum of d s sub lambda a sub lambda cos lambda phi plus b sub lambda sin lambda phi, but that d and that a sub lambda and b sub lambda are all constants, so we can multiply the d into the parentheses. And similarly, looking at the other infinite sum, we can multiply the e into the parentheses. And that reduces the number of arbitrary constants, so we will do that when we write our final general solution. So this boxed equation, equation 9, is the general solution for Laplace's equation in cylindrical coordinates, assuming no z-axis dependence. we find it has a constant A naught term, a B naught the natural log of S term, an infinite sum of S to the lambda times A sub lambda cos lambda phi plus B sub lambda sine lambda phi, and then we can add S to minus lambda times C sub lambda cos lambda phi plus D sub lambda sine lambda phi. And with that, we have the general solution for cylindrical coordinates. So now we can take this equation 9 and use it in problem 4.22. Having discussed linear dielectrics, boundary conditions of linear dielectrics, and separation of variables, let's look back at the problem statement. A very long cylinder of linear dielectric material is placed in otherwise uniform electric field E0. Find the resulting field within the cylinder, given that the radius is A, the susceptibility chi-e, and the axis is perpendicular E0. To begin, we're going to say let E be E0 x, and that's just the initial electric field. So initially the electric field is going to go along the x-axis, and the reason is we can pick on the yz plane which direction we want the electric field to go. We were only told it was perpendicular to the z-axis of our cylinder. And then, recalling that since there didn't say there were any free charges on or in our linear dielectric, we'll assume that there are no free charges. So if there are no free charges, no free volume charges by the first equation we found, there cannot be any bound charges. So rho is 0 inside this cylinder. And we're going to choose the yz plane to have a potential of 0. Now, at first this might seem like a question of whether it could be allowed or not. And the answer is, think before we add the cylinder, and we see that the yz plane basically is an equipotential, because the electric field is going perpendicular to it. So it's an equipotential plane. And then when we add the cylinder, we said there are no bound volume charges, so the only thing that could happen are bound surface charges. And the bound surface charges will form, as drawn in the bottom right corner, but for every negative charge that forms on the side where the electric field is entering the linear dielectric, a positive charge is going to form opposite of it to cancel the effect. So we see that this symmetry between them results in the yz plane not having a change in voltage. They cancel. Their voltage cancels in the yz plane. So the yz plane continues to be an equipotential even after we put the cylinder in there. So we will choose to let the entire yz plane be defined as the zero potential. So we can now write that rho is 0 inside and outside, and therefore we can use Laplace's equation. And that means everything we did with separation of variables can be used again. We also are going to want to look at voltage far from the cylinder before we continue. So we know that the initial electric field pointed is E0 x hat, and then we can integrate to find the initial voltage. So we integrate minus E0 dot dl, and then we go ahead and get minus E0 x plus c. However, we said let v of 0 be 0 along the yz plane, which is when x is 0. So plugging in that restriction, we can eliminate the arbitrary constant. So we find v0 is minus E0 s cosine phi, because we want to write it in cylindrical coordinates. Given this, adding the cylinder might change the voltage locally, but we'd expect, since it doesn't have any charges in it, that if you get far enough away from the cylinder, you won't notice the effect of it. So we expect that V is going to go to V0 for large values of S when we go far away from this cylinder. And we will use that as another restriction on our problem. So now we can look at the boundary conditions. We're going to recall equation 2, which basically said that we have continuity of voltage across a boundary of the linear dielectric in the outside free space. We are also going to recall equation 3, which connected the partial across the boundary. So we now know that the partial of V with respect to S times E0 outside is going to equal the E of the dielectric partial of Vn with respect to S, and that's at the boundary. And then we can say that V is going to be finite at s equals 0. We know that has to be true because we said anywhere where x is 0 has to be 0, and we know then that at s equals 0, since x is s cosine phi, then at s equals 0, v is going to be 0. I say finite just because that may not in general be true that it's going to be 0 volts there, but a lot of times it holds it's finite, and that it'd be unphysical to expect that given an E0 field that you're going to generate an infinite voltage inside the cylinder. So we will eliminate any terms that generate that problem. We also are going to use the statement that at x equals 0, V0 has to be 0. And the final one, that we want our voltage to go to minus E0 s cosine phi when s goes far, far away from A. Hence, we're going to reference the general equation 9 and set equal to V0. But then we're going to apply the restrictions, starting with restriction 11. And equation 11 said that it needs to be finite. Looking at these terms one by one, the logarithm of s will go to minus infinity at the origin. Hence, that term cannot exist. It has to be a 0 coefficient. Similarly, this s to the minus lambda will go to infinity and minus infinity. So the coefficients in that expression have to all be 0. So c sub lambda is 0 and d sub lambda is 0 for all lambda. Now, you could say, well, couldn't there be a way where C1 might be just the right coefficient to cancel D2 or something like that? However, the answer is it can't be, and one reason is that because cosine of phi, sine of phi, cosine 2 phi, sine of 2 phi, they're all orthogonal, that you can't build a set of C lambda and D lambda which cancel out. So we can eliminate these out of the fact that we do not want a physical answer at s equals 0. Another one we can eliminate is the A0, because we let for v is 0 be 0 when we say that x is 0. So putting that in, that falls out. We find that if basically this A0 constant term basically dictates where would be different if V0 at x equals 0 was not 0. We'd have a number there. But we're eliminating that by putting it 0 at that point. And that gives us equation 13. This is a simplified voltage in. And recall, our goal is to find the electric field inside this cylinder. However, we don't know A lambda yet, and we don't know what the B lambdas are yet. And there are so we need to find all the A lambda and all the B lambda terms before we can go ahead and find the electric field inside. So we will need to look at the voltage outside the cylinder to get the next part of this. Looking at the voltage outside the cylinder, by the same argument, F0 is 0, again recalling 12, and recalling boundary condition 10, we can say that V needs to go towards E0 s cosine phi. Now if we think about this, the logarithm cannot be allowed, because if you go for large values of s, the logarithm does not go to 0, the logarithm grows. So that term has to go away, and so the only way to make it go away is to set its constant, its coefficient g0 into 0. Similarly, these s to the lambda terms are going to be growing as you move further away from the cylinder, so they're not going to disappear. We said the s to the 1 of the cosine phi is okay. So there's one term that's allowed. The F1 is allowed because we need it, because the voltage is not going to 0, it's going to minus E0 s cosine phi. The rest, though, the F of lambda for the higher lambda values and G of lambda for all lambda values 1 and greater, need to go away because they can't be allowed in the solution. And that gets us to equation 14. Now we can note the s to the minus lambda terms are okay because as you move far away from the cylinder, the s to the minus lambda causes those terms to die out. So those terms will disappear if you move far away from the cylinder, and they're acceptable for that reason. We can now go back to our boundary conditions. We've used 3 of the 5, so our next goal will be to use the 2 that remain, and we will start with Vn equals V out at the boundary s equals A. So on the surface of the cylinder, we can write V in and we can write V out. and since we said Vn equals V out at the outside edge of the cylinder at little a, then we can just go ahead and equate them. And then after equating them, we can look at it and decide to move everything to one side of the equation. So we'll just move everything to the left-hand side of the equation. And we can also combine things. I've chosen to go ahead and combine things by putting everything in front of cosine phi together, and everything in front of cosine lambda phi together, and everything in front of sine lambda phi together. And this is an advantage because recall that in general, cosine phi is not going to be 0, sine lambda phi is not going to be 0, cosine lambda phi is not going to be 0. So to get this to be 0 in every case, then whatever's in the parentheses in front of each trig function has to be 0. So we can look at it and say that in general, a1 plus e naught all times little a minus h of 1 times little a to negative 1 has to be 0 in general for this to hold. Remember, since cosine lambda phi and sine lambda phi are all orthogonal, they can't. There's no interaction between them that allows them to cancel out. So we can use that to get our first our first statement, 15a, and this connects our h of 1 and a of 1. Similarly, we can look inside that first summation, and we see that a lambda little a to the lambda minus h sub lambda little a to the minus lambda has to equal 0. So we can write that one, and that's 15b. And again, we can look at the last summation, and we say that b sub lambda times little a to the lambda minus I sub lambda times little a to the negative lambda has to be 0 in general. And so we can write that as 15c. And those are 3 equations. And that's not enough, since we don't know, we have 2 unknowns in each equation. That's not enough to solve any of these. But we can go ahead and get the other boundary condition, use it to get a second set of equations with 2 unknowns, and then combine them and solve them. So that will be the goal. So let's now go ahead and look at the last boundary condition. So the last boundary condition was equation 3 we found quite a while back. It said that epsilon naught, the partial V out with respect to S, equals epsilon of the material, partial of V inside the material with respect to S, evaluated at the surface of the material, which in this case is going to be S equals little a. And so we can rewrite that equation into a form that's going to be a little bit easier to use, and I just go ahead and wrote that out. And now we can recall Vn and V out. They were equations 13 and 14. And recalling them, the first thing we'll need to do is take the partials of them. So we'll take the partial of Vn, and that's straightforward. All you do is you do term by term, take the partial derivative with respect to S, and the S to the lambda just becomes lambda S to lambda minus 1. Similarly, we take the partial of V out, and that just gets us the first term. Partial of with respect to S is 1, and the rest of the terms, partial of S to minus lambda is just minus lambda times S to minus lambda minus 1. And that gives us Vn and V out as partials, and then we can go ahead and plug it into the equation in the top right hand corner of the screen. And that gives us this. And of course, this equation is rather ugly, and so attacking it directly would be painful, but we call the same trick we used on the last boundary condition was to write it in terms of everything in front of the cosine of phi, everything in front of the cosine lambda phi, everything in front of the sine lambda phi. So we can go ahead and do that. And first, I will just write up the same equation as before, and then I will go ahead and isolate them by the trig function they have. So we find the first equation we'll have is epsilon times a1 plus epsilon naught e naught plus epsilon naught little a to minus 2 times h of 1. And we find that that has to be 0 in general because cosine of phi is not 0 in general and the terms are orthogonal. So let's look at that. And so first thing we're going to do is we're going to want to get the h by on its own side. We're going to want to make this equation look like the equation 15a we just found. So I will go ahead and multiply by little a across the equation, and that gets us into the form of nearly into the form of 15a, and so that's how we're going to handle it. And similarly, we can go ahead and look at the other two terms. This is again the equation with the terms isolated, and then we can go ahead and, looking at the infinite sum of the cosine lambda phi, we have an epsilon a sub lambda a to the lambda minus 1 plus epsilon naught h sub lambda a to the minus lambda minus 1, and we can say, well, if those two things sum to 0, they have to be opposites. They have to be one has to be the negative of the other. And then, of course, we can rewrite it to make it look more like the original equation by dividing by epsilon naught and multiplying by little a. So that's what we'll go ahead and do. We'll call that 16b. And we can go ahead and do basically the same thing for the b sub lambda and I sub lambda. Looking at that term right there, we can say that they have to be opposite. So epsilon b sub lambda a little a to the lambda minus 1 equals negative epsilon naught I sub lambda a to little a to the minus lambda minus 1, and that has to be true for all lambda greater than 0. And again, we can just go ahead and make it look a little bit more like 15c by dividing by epsilon naught and multiplying by little a, and so it gets us 16c. Now, we have two sets of equations, and each equation has two unknowns. We can solve that. That brings us to these two equations. So we have two equations with a1 and h1 in them, so we can now solve for a1. So first thing we're going to do is just substitute h1 out basically by saying the equations equal to each other. That's the first step. Now we can divide by little a, and that will get us, and of course we can move the e naughts over to make to isolate the a1. And now that we have a1 isolated, we can just divide by the epsilon over epsilon naught plus 1, and that gets us a1. Now, recall we don't really want h1, we don't really need it because we only are interested in the voltage inside the cylinder. The problem didn't ask about outside the cylinder. And now we should stop for a moment and think about our use of the permittivity of the material epsilon. We don't really want epsilon because the problem statement gave it to us in terms of susceptibility chi, the electric susceptibility, but it didn't give it to us in terms of the permittivity of the material epsilon. So we should replace epsilon with epsilon naught times 1 plus the electric susceptibility, and we can go ahead and do that. And that is equation 17a. Now we have a1 solved. It's minus e naught over 1 plus chi over 2, and now all there is to do is to repeat this process, solving for a lambda for the other lambdas and solving for b sub lambda in general. Looking at 15b and 16b, we can do the similar trick of setting the h sub lambda equal, and doing that lets us solve this pretty quickly. Now, on the next step, we will go ahead and say little a is not 0, so we'll divide by it, and we will divide by capital A, assuming that capital A sub lambda is not 0 either. And that gives us that 1 equals minus epsilon over epsilon naught. That is a problem, because if you think about that, we just said epsilon was epsilon naught 1 plus chi, and if you look at that, this 1 equals minus epsilon over epsilon naught says that the susceptibility needs to be negative 2, chi needs to be negative 2, and chi is a positive number. It's 0 for free space, basically. You could treat it like that, and it would be positive for any linear dielectric. So we can't have chi being negative 2. So this epsilon equals minus epsilon naught is a contradiction. And that makes us look back at our assumptions. We assumed that little a sub lambda was not 0, but if little a was 0, then we're basically saying there wasn't a cylinder. So that's kind of a that's not really a physical case, so we can get rid of that. The only other assumption we made was capital A sub lambda was not 0. So that has to be the case. Capital A sub lambda has to be 0, and that means h of lambda is 0 as well for lambda greater than 1. And we can write that as 17b. So we've managed to eliminate all the a sub lambda terms other than a sub 1. Now, the last thing to do would be look at the b sub lambda terms. Taking 15c and 16c. Again, combining them by setting I sub lambda little a to the minus lambda equal. And again, we can divide by b sub lambda and little a sub lambda, assuming b sub lambda is not 0. Yet we hit the same contradiction. We're again finding that the only way b sub lambda could not be 0 would be if the susceptibility chi was -2. But again, chi is a positive number for linear dielectric. We have that same contradiction, so b sub lambda must be 0 for all b sub lambda. And that is what we found. So that would be 17c, and we now have found a1, we found a sub lambda for the other lambda values, and we have found b sub lambda for all the lambda values. So now we can go ahead and, looking back at our voltage N equation, we can solve this problem. Recall 13, which was the voltage N after we used the first 3 boundary conditions on the problem. And now we can substitute in 17a, b, and c. And doing so, we can simplify this down and say Vn is just SA1 cosine phi as the other a sub lambda, and all the b sub lambda terms were zeros. And we know what A1 is, we found it, so we can go ahead and plug that in. And that says Vn is just minus E naught S cosine phi over 1 plus chi over 2. And to get the electric field, because we were asked about what the electric field was inside the cylinder, we need to combine this and write, we probably want to write it in terms of Cartesian coordinates, because what we want to do is take the negative gradient of the voltage to get the electric field. So we'll rewrite S cosine phi as x, and then just take the negative gradient of it, and that gets us E interior. And looking at it, we think E naught x hat, we've seen that before, because when we define the x-axis, we put the x-axis in the direction of the initial electric field, E naught. So really, this E naught x hat is just E naught vector. So our final answer is the E interior is just E naught vector divided by 1 plus chi over 2. So much like problem or example 4.7 with the dielectric sphere in the uniform electric field, for the dielectric cylinder, the linear dielectric cylinder, we find that the electric field inside the cylinder is just the electric field E naught, but the magnitude is divided by 1 plus chi over 2. So the magnitude is reduced, but the field remains constant inside the cylinder and pointed in the same direction as it did initially. With this, we've solved problem 4.22.